In this video, we're going to take a look at the second electrolysis problems worksheet, more electrolysis problems. This is good to review for your test as well as for your final exam. We have four basic tools to solve electrolysis problems with. One tool is the volume ratio. When you perform electrolysis of water, you decompose the water into hydrogen gas and oxygen gas, and when collected, you'll get 2 milliliters of hydrogen gas for every 1 milliliter of oxygen gas. You get twice as much hydrogen as oxygen, and that's due to the balanced equation for the decomposition of water. In the balanced equation, 2 water molecules decompose to give 2 hydrogen molecules and 1 oxygen molecule. So you can see there the 2-to-1 ratio in molecules, and therefore the 2-to-1 ratio in volumes for the gases produced. There's also a mass ratio. We got this by looking at the periodic table and using that same chemical formula. The mass ratio involves water now as well as hydrogen and oxygen, and it tells us that if you decompose 9 grams of water, you will produce 8 grams of oxygen and 1 gram of hydrogen. So you get more oxygen now than hydrogen when you're looking at masses, and that's because the mass of an oxygen atom is much larger than the mass of a hydrogen atom. Then there's the law of conservation of mass. Law of conservation of mass. When you look at our chemical reaction, the water is what we begin with, and the hydrogen and oxygen are what we end with. So by the law of conservation of mass, the mass of water decomposed has to equal the mass of the hydrogen gas produced plus the mass of the oxygen gas produced. Those two masses must add up to give the mass of water by the law of conservation of mass. The fourth tool that we have comes from our solubility chart. On the back, we have these densities. This is in your science booklet. It's also on the web where we have our course website. So we'll use the density of hydrogen and the density of oxygen and the density of water. So we have densities as a fourth tool. For hydrogen, that density is given as 8.99 times 10 to the minus 5 grams per milliliter. And for oxygen, the density is 1.33 times 10 to the minus 3 grams per milliliter. And that's given at standard temperature, 20 degrees Celsius and 101 kilopascals pressure. Alright, let's jump in and begin with the first question. So Jack has collected 22 milliliters of hydrogen gas by electrolysis. What mass of hydrogen gas was collected? So when we stand back and look at that, we recognize we were told the volume of the hydrogen, and now we want to know the mass of the hydrogen. To go from a volume to a mass, we're going to use the density as a unit multiplier. So we'll start with the volume, 22.0 milliliters of hydrogen, and we'll use that density to get rid of the milliliters of hydrogen, so trying to get rid of those units, and we'll replace with grams of hydrogen because we're trying to find the mass, and mass is measured in grams. The density, as we just saw, was 8.99 times 10 to the minus 5 grams for every 1 milliliter. So now we can grab a calculator, and I'm going to use the scientific notation button on the calculator. On this calculator, which is a Casio button, there's a little times 10 to the power of X button, which is for scientific notation. On Texas Instruments calculators, like this graphing calculator, there's a button somewhere that says EE, and here it's in blue right above this comma, EE. And on Sharp calculators, it'll be a button that says EXP, EXP, and those are all going to do the same thing. They'll let you type a number using scientific notation. So on this calculator, we'll go 22 milliliters times 8.99, and then I'm going to press that scientific notation button, and when I do, I say to myself times 10 to the power of, and that's whether you're pressing the EE button, the EXP button, or on this calculator, the little times 10 to the X button. So when you press it, you say times 10 to the power of, and now you just type in the exponent, -5. Make sure you're using -5, which is not the same as -5, right? Those are two different things. Equals, and we get 1.9778, which will round off to just 1.98 times 10 to the -3. And that will be grams of hydrogen. Now if you wanted to write that as 0.00198 grams of hydrogen, that would be perfectly acceptable. Okay? I'm going to leave my answer in scientific notation. What volume of oxygen was produced? Well, we knew we now know two things. We know the volume of hydrogen in the original question, and we know the mass of hydrogen. To get the volume of oxygen, I'm going to have to use the volume ratio that we mentioned earlier, and I'll start with the volume of the hydrogen, 22.0 milliliters of hydrogen. And my volume ratio will let me get rid of the mils of hydrogen and replace it with milliliters of oxygen, because I know that there's 2 mils of hydrogen for every 1 mil of oxygen. So it's going to be half as much oxygen. So 11.0 milliliters of oxygen will be collected. We now know the volume of each gas, and we know the mass of the hydrogen. Part C, what mass of oxygen was produced? Well, suddenly we've got more than one way to answer this. Using density, we could do what we did for hydrogen. We could take the volume of the oxygen, 11 milliliters of oxygen, and we could use its density to get rid of the milliliters of oxygen and switch to grams of oxygen. And that would be using the density 1.33 times 10 to the -3 grams for every 1 milliliter. Grabbing a calculator, 11 times 1.33 times 10 to the power of -3 is 0.0146 grams of oxygen. There's another way we could have done that, though, so let me put an OR here, and you'd really only have to choose one method. You don't have to do both, but you should understand both. Since we knew the mass of the hydrogen back in Part A, we could have started with that. We could have taken the 1.98 times 10 to the -3 grams of hydrogen, and looking for the grams of oxygen, we could use the mass ratio from above. We can get rid of grams of hydrogen and replace with grams of oxygen. Looking at my ratio above for masses, there's three quantities: water, oxygen, hydrogen. We're using oxygen and hydrogen, so we're going to use those two numbers, 8 and 1. So there's 8 grams of oxygen for every 1 gram of hydrogen. And now 1.98 times 10 to the -3 is the mass of hydrogen. Times that by 8, and we get 0.0158 grams of oxygen. And notice that depending on which method you chose, we get a slightly different answer in those masses. Okay? Either one will be fine though, but depending on which one you chose, you'll get one mass or the other. As long as your work is shown, this will be fine. Notice they're very close, 148 and 158. Sorry, 146 and 158, but they're not quite exactly the same. Part D, what mass of water would decompose? Well, we've got more than one way to do this. Perhaps the easiest way would be to use the law of conservation of mass. We said up above that the law of conservation of mass tells us that the mass of water decomposed would equal the sum of the masses of the two gases. Since we now know the two gas masses, it's pretty easy to get the mass of water decomposed. So we could say the mass of water is equal to the mass of the oxygen plus the mass of the hydrogen. So in this case it's going to be and I'll use the first mass that I had, 0.0146 grams of oxygen plus 0.00198 grams of hydrogen, and if we just add those together, 0.0146 plus 0.00198, and of course you could have left it in scientific notation, that's fine, 0.0166 grams of water would be my answer there. The other way you could have done that would have been to use the mass ratio again, and you could have started the mass ratio with either the mass of oxygen or the mass of hydrogen. Let me show you it using the mass of oxygen. So we could have taken 0.0146 grams of oxygen, that's what we calculated just above, and using the mass ratio we'd get rid of grams of oxygen and replace with grams of water. Up above in our mass ratio, remember there's three things in the mass ratio. There's water, oxygen, and hydrogen. So now I'm looking at water and oxygen, 9 to 8. So down here in my unit multiplier, there's 9 grams of water for every 8 grams of oxygen. And this answer should be pretty close to the one we just got. So 0.0146 times 9 over 8, 0.0164, which is very close to the answer we got by just adding the masses together. So there's more than one way to do it, and your answers again are just slightly different depending on which method you chose. Part E, what volume of water decomposed? Well, the only way to get the volume now of water would be to use its density. So we'll take the mass of water, I'll use my first mass, 0.0166 grams of water, and I'll use the density of water. I didn't mention it earlier because this is one that we should all just know for sure. Get rid of grams of water, switch to milliliters of water, and its density is 1 gram per milliliter, so the number stays the same, 0.0166 milliliters of water. So there you have it, a multi-step problem involving electrolysis, and we solved it using volume ratios, mass ratios, law of conservation of mass, as well as density calculations. So people who find this problem difficult, usually they find it difficult because of the different ways we can solve the problems, and as we saw, some of the problems can be solved in more than one way, which for some people is just even more confusing. Explain why water is an example of a compound. Well, to be a compound, you have to be a pure substance, and you have to be made of more than one element. So we can just say here, water is a pure substance made of 2 elements, hydrogen and oxygen. And that's enough. The definition of compound, a pure substance made of 2 or more elements. Okay, we'll jump in and we'll do one more problem here. Catherine allowed 0.25 milliliters of water to decompose by electrolysis. So what mass of water decomposed? If we know the volume of the water and we want to know the mass of the water, there's only one way to do that, and that would be with its density. So 0.25 milliliters of water. We'll get rid of milliliters of water and replace it with grams of water, and that of course is density, grams and milliliters. So 1 gram per milliliter, and the answer stays the same, 0.25 grams of water decomposed. What mass of oxygen would have been produced? Well, there's only one way to do this at this point. We know the volume of water, we know the mass of water, and now we're asked for the mass of oxygen. The only way to do that right now would be to use the mass ratio. In the mass ratio, we know that there's 9 grams of water for every 8 grams of oxygen, since those are the two substances we're dealing with here. So I'll take my mass of water, 0.25 grams of water, and I'll get rid of grams of water, put it on the bottom of the multiplier, and replace it with grams of oxygen, since that's what we're trying to find. Those units will cancel out, and we're left with grams of oxygen. The mass ratio says you get 8 grams of oxygen when you decompose 9 grams of water. So, grabbing a calculator, 0.25 times 8 over 9, 0.222, repeating, so I'll just say 0.22 grams of oxygen would be produced. What mass of hydrogen would have been produced? Well, we now have two different ways to do this. One method would be to use the same approach we did just a moment ago. So we could have taken 0.25 grams of water and go back to our mass ratio, but this time we'd be focusing on the water and the hydrogen. So for every 9 grams of water, you get 1 gram of hydrogen, and that will be my unit multiplier. So coming down here, we can get rid of grams of water and replace with grams of hydrogen. You get 1 hydrogen gram for every 9 grams of water decomposed. So 0.25 divided by 9, 0.028, or 0.028 grams of hydrogen would be produced. Now, the other way to do it would have been to use the law of conservation of mass. The mass of the water decomposed was equal to the mass of each gas added together. So if I want to know the mass of hydrogen, I could take the mass of water and subtract the mass of oxygen. That would give me the mass of hydrogen that was produced. So we could have said, or another way to do this, the mass of the water, 0.25 grams, minus the mass of the oxygen, 0.22 grams, equals 0.03 grams of hydrogen. And that, again, that's the mass of the water minus the mass of the oxygen gives me the mass of the hydrogen gas produced. Now, because we're subtracting here, we round off by decimal places and we're left with just 0.03, whereas up above multiplying, dividing, I kept two significant digits there, 0.028. What volume of oxygen would be produced? Well, right now, there's only one way to do that. That would be to take the mass of oxygen and use density to find volume. Because we don't know the volume of hydrogen yet, we can't use the volume ratio, and the volume of water is not going to help us find the volume of gases. There's no volume ratio that involves water. So therefore, we'll have to do this with a density calculation. We'll take the mass of the oxygen, 0.22 grams of oxygen, get rid of the grams of oxygen, and switch to milliliters of oxygen. 1 milliliter is 1.33 times 10 to the minus 3 grams, and that's the density from our solubility chart on the back. So now, taking 0.22 and dividing by 1.33 times 10 to the power of negative 3 equals 165 milliliters. That's an extra significant digit, but that's okay for this. 165 milliliters of oxygen would be produced. What volume of hydrogen would be produced? Well, we could do exactly the same approach. We could take the mass of hydrogen, 0.028 grams of hydrogen, and we could do a density calculation to get rid of the grams of hydrogen and switch to milliliters of hydrogen. The density for hydrogen is 8.99 times 10 to the minus 5 grams per milliliter. And so 0.028 divided by 0.028 divided by 8.99 times 10 to the power of -5 equals 311 milliliters of hydrogen. And those would both get full marks. However, there was another way to get the hydrogen's volume, and that's because we already knew the oxygen volume. We had just found oxygen's volume to be 165 milliliters. So we could have found the hydrogen volume with the volume ratio. We saw that up above. For every 2 mils of hydrogen, you get 1 mil of oxygen gas. The volume ratio only applies to oxygen and hydrogen. Water is not part of the volume ratio. So 165 mils of oxygen, we could have got rid of mils of oxygen and switched to mils of hydrogen using the 2-to-1 ratio that we saw above. 2 mils hydrogen for every 1 mil oxygen. And that's going to give me an answer which is just a little bit bigger. It's going to give me 330 milliliters, 165 times 2, 330 milliliters. So not quite, but close to the answer using density, but there's a small difference. So using whichever method you use, you'd get full marks as long as your units, or as long as your unit multipliers are shown, your work is shown. So there we've done 3 of the 4 problems on this side of the worksheet. There's 2 sides to this worksheet with some other questions. Let me just scan over here. Is there anything else on here that's a little bit more challenging? In these questions 5 and 6, I'm giving you clues as to how many unit multipliers to use. Maybe I'll take one of them and help you with it. Number 5, what volume of water in milliliters would you need to get 10 liters of hydrogen gas by electrolysis? And I'm going to suggest that you just do that with a string of unit multipliers. You don't need to do it as a bunch of different steps, although you could. I'm going to start with my 10 liters of hydrogen gas. The question is, what volume of water do I need to do that? So what I'll do first is switch from liters to milliliters of hydrogen gas. Then I'll use the density to go from milliliters of hydrogen to grams of hydrogen. Then I'll go from grams of hydrogen using the mass ratio to grams of water. And then, since the answer was in milliliters, I'll just do one more multiplier, and I'm just going to squeeze it in here. It's getting into my other question, but so be it. I'll get rid of grams of water, and using water's density, I'll switch to milliliters of water. Alright, so the first multiplier here is just liters to milliliters conversion, and that's straightforward. 1 liter is 1,000 milliliters. The second multiplier, grams and milliliters for hydrogen, is its density, so there's 8.99 times 10 to the minus 5 grams for every milliliter of hydrogen. The third multiplier comes from our mass ratio, which we saw earlier. For every 9 grams of water that decompose, you'll get only 1 gram of hydrogen gas. And then finally, using the density of water, there's 1 gram of water for every 1 milliliter of water. Its density is 1 gram per milliliter. So with the calculator now, 10 liters times 1,000 milliliters per liter times 8.99 times 10 to the minus 5 grams per milliliter times by 9, and we get 8.09 milliliters of water. So if you decompose 8.09, or just a little bit more than 8 mils of water, you'll end up getting 10 liters of hydrogen gas. And that's why there's no law of conservation of volume. You get a huge volume of gas from just a tiny amount of water decomposed. So I hope that helps with electrolysis of water problems. There's a few other questions on here similar to that, and these are definitely going to be on your test and on your final exam.